This is a recording of a presentation I held at the Swedish Institute for Social Research at the Stockholm University, November 4th. Before I'll get to the weighted effect coding, I'll start with a little history. And it starts with an article written by Sweeney and Ulvring back in 1972. It's called "A Transformation for Simplifying the Interpretation of Coefficients of Binary Variables in Regression Analysis." It's a quite a long title, and it was published by in the American Statistician, by the way. It deals with weighted effect coding, but it was written down in rather theoretical terms, and there was no software attached to it. And I think as a consequence of that, the article didn't get that much attention as it deserved, actually. I looked it up. It was cited about 42 times, according to Google Scholar. And for such an article, that citation number is way too low. But it is the start of our own journey to construct software for this very nice way of dummyifying variables, dummyifying categorical variables. Before I explain to you the weighted effect coding, we first take a look at the most popular way of coding categorical variables. And I have here a very straightforward example. It's about the relationship between education and the body mass index. And as we can see, the people with the lowest level of education, they have on average a body mass index of 26. And over here we have the highest educated people. I left out the categories in between just to keep it as simple as possible. And you can see that the highest educated people have a body mass index of 24. Now, if we use dummy coding, then the resulting estimate of that procedure will yield 2. So that's simply the difference between the lowest and the highest educated. Of course, it depends on which way you have dummy coded the variables. It can be 2, and it can also be -2. It's just the choice of which one of the categories serves as a reference category. So with dummy coding, we just estimate the difference between 2 categories or more categories of a categorical variable. And the statistical test is also related to that very difference between 2 known categories. So that's a very useful way of coding coding categorical variables. And it is very practical when you got a directional hypothesis saying that the highest educated will have a lower body mass index than the lowest. Then dummy coding is perfect. Now here we have something else. This is called effect coding. And with effect coding, we have a different point of view, actually a different point of reference. As you can see, we have again the lowest educated people over here. They have a body mass index of 26 on average, and we have the highest educated over here with a body mass index on average of 24. And as you can see over here, we have quite different numbers. In the previous slide, this was coded 0. And it was coded 1, but now it changes. We have a -1 for the lowest category. We have a 0 for the point where we got 25. I come to that. And we have over here the code 1 for the highest. Now, if we go exactly in the middle of this graph, we have the code 0, and of course we find the number of 25. It's exactly in the middle of this graph. So if we would take 25 as a point of reference, which is the reference point in effect coding, if we compare the lowest educated with this so-called grand mean, then we get 1. And if we compare it to the highest educated, we get a -1. So we just split the effect of 2 from the previous slide. We just divided it, and we took the grand mean as a point of reference. Now, if you do so, then you assume that the two categories, being the lowest educated and the highest educated, we assume that the number of observations in those two categories are equal. And we do not have to assume that for our sample data. It can be that those two categories are a little bit different due to some random fluctuation due to the fact that we have a sample. But if we assume that in the population to which we like to generalize our hypothesis, if we assume that in that population those two groups are more or less equal, then effect coding is a wonderful way to estimate your differences. So in the literature, you will find that effect coding is very suitable if you have so-called balanced data. And with balanced data, we mean that all the categories we have under investigation have more or less the same number of observations. Then effect coding is perfect. Okay, now we come to the article written by Sweeney and Ulvring, because they say, okay, that may be true for balanced data, but in many instances, as we can see right now, when we turn to the next slide, here we have the slide that deals with weighted effect coding. That was the subject of the article written by Sweeney and Ulvring back in 1972. In this example, we have again the lowest educated, and they have a body mass index of 26 on average. And we have the highest educated respondents over here, and they have on average a body mass index of 24. Now, in this situation, I took into account the different number of observations. For this example, I have set the number of highest educated people to be 500. So we have 500 highly educated respondents. And for the lowest educated people, I have only 100. So we have a total sample size of 600. Now, if I would multiply 26 by 100 and I would multiply 24 by 500 and I would sum these two results and I would divide it by the sample size being 600, then I would end up with 24.3. So that's the formula calculating a sample mean. And that is quite different from the unweighted mean or the grand mean, which appeared to be 25. And that is exactly what Sweeney and Ulvring pointed to. If you got so-called unbalanced data, and with unbalanced we mean that the number of observations per category is quite different. If that is the case, then your sample mean will be much more informative than the grand mean, because the grand mean assumes equal number of observations. But as we deal with survey data or observational data, then we often have the situation that we have quite different numbers of observation, and we in that instance we might like to take that into account. So if we would want to take that into account, we will end up with estimates for the difference between the lowest educated and the sample mean will be 1.7, and the difference between the sample mean and the average body mass index amongst the highly educated will be minus 0.3. So that's quite a different test compared to effect coding. And as you can see, the thing is that with weighted effect coding, we use as a coding for the lowest educated, not -1 as an effect coding, but we have replaced that by a weight, and that is equal to the number of observations in the highest category divided by the number of observations in the lowest category. So that's our weight factor we have to take into account. So if you use weighted effect coding, if you would use that way of to have your dummy variables in your regression equation, if you like it this way, then the estimates, the resulting estimates from that regression analysis will relate to our sample mean, and that is especially useful when you have different numbers of observation. So if you got unbalanced data. Now, what I did in the previous slides was, quite straightforward. We had only two categories, but you can expand that framework of using weighted effect coding to any number of categories you would like. So for this situation, I expanded it by adding just one educational category. So we have lowest education, middle education, and highest education. And as you can see, this is a regression equation that normally has a problem because we have an observation for the sample mean, which is equal to the intercept, and we have three parameters over here, which normally will lead to a redundancy, and one of the categories would be omitted from the equation. But weighted effect coding uses a restriction that says that if we take the sum of all weighted parameters, meaning that we weighted the parameters with the number of observations, then if we do so, then we'll get 0. So recall that in the previous slide, one of the weights was negative. So we have negative weights and we have positive weights, and if we add them all up, then we'll end up with 0. That is the weighted effect coded restriction. And if we impose that upon the regression equation, we are able to estimate the parameters. Okay, well. As an example, I will show you now the outcomes of dummy coding, effect coding, and weighted effect coding for an example in which we use three categories of education, which are quite different in the number of observations. As you can see over here, we have 698 lower educated, and we have over 1,000 highly educated respondents, and we have also a middle category. Okay, if we use dummy coding, then you see that for the intercept we have an average body mass index of 26.15, and that number relates directly to the low educated respondents, which were used as a point of reference. And we have over here two estimates that relate to the difference between the low educated and the middle educated and the high educated. So the high educated have a body mass index that is on average 1.85 body mass index points lower compared to the low educated. And as you can see, both differences are significant. So if you would like to test a hypothesis that the body mass index is higher if you are higher educated, then you can test that hypothesis very well with dummy coding. Okay, there is a different way of approaching this. We can also use effect coding. If we just disregard the number of observations in all categories and we say, okay, in the population this will be probably equal, then we can use effect coding, and we'll get as a result 25.14. which is the unweighted mean or the grand mean, and over here we have the differences um, of all categories, of all three categories from that grand mean. So if you take the low educated, there are one body mass index point on above 25.14, and we have the middle educated, there are 0.16 below that grand mean, and we have minus 0.84 for the highly educated, and they have also a minus sign, which means that they also are lower on average on their body mass index scale. Please notice that if you add these three estimates, you will end up with a number equal to 0. And that is typical for effect coding, because we do not take into account the different number of observations. We assume that all categories are basically just as big, and as a consequence, the three estimates will always add up to 0. Okay, now assuming that all categories of education are equal, well, that is way off the mark, because in our sample they are definitely not equal to each other. So effect coding is probably not the right way to approach this problem. So as a last column, we have the outcomes for weighted effect coding. As you can see, the numbers are quite different. We have 24.98 over here, and that is exactly the sample mean in our data. So if you would just take our sample and ask for the mean of body mass index, you will get 24.98. And as you can see, here we have quite different numbers of the estimates. We have, for instance, the middle educated, which do not deviate from the sample mean. Actually, they are exactly equal to the sample mean. And we find that the lowly educated are about 1.17 points above that sample mean, and we have the highly educated, which are minus 0.68 above that sample mean. And you may also notice that the t-values over here and the t-values over here are quite different. It's a different test. So if you like to take into account the different numbers of observations, and I believe that that would be a wise thing to do, because the educational categories do not have equal numbers of observation, then weighted effect coding is superior to effect coding. And as a last remark, please notice that the explained variance of all three models is exactly equal. It's just that we change the point of reference, and we do not change the power of prediction of these models. They are all three equal. It's just the way you like to use the point of reference you would like to use. That's the only difference. And all statistical tests, of course, are related to that choice of point of reference. Okay, of course, we can expand our model, and we can use some control variables like males and females included. We can include age, and maybe we like to include some other variables as well. That's no problem for weighted effect coding. As you can see, you can put in as many controls as you like. The sample mean is still depicted over here. It's still equal to the intercept. I have to add that if you would like to have this number again in the intercept, you have to mean center this variable, and you have to weighted effect code males and females and the year of interview as well. And if you do so, you will get the intercept equal to 24.98. The numbers over here depict the difference, the deviation from the sample mean. as you can see, there are quite large differences, and if we add these estimates, you will notice that it doesn't add up to zero. It adds up to zero actually if you take into account the different numbers of observation. So if you weight 0.85 by 689 and you weight 0.12 by 1419 and you weight minus 0.64 by 1197, you will get zero. I mean, that's the restriction in weighted effect coding. As you can see, for the difference between males and females, there are almost each other's counterpart, which is also true for these estimates, and they almost add up to zero. That means that despite the fact that we weighted effect coded these variables, it doesn't have much influence on the estimates because the number of observations is quite equal. So if you would like to take into account the numbers of the different numbers of observation, it really makes a difference when you got really differences in observation. And when you take a look at the male-female ratio in the population, it's about equal. So the difference between effect coding and weighted effect coding will be rather small. And the same goes for the number of observations in your sample. But if we take a look at the differences between the educational categories, it really makes a difference. So weighted effect coding is especially efficient if the number of categories is different. Was the first part of my presentation dealing with the weighted effect coded categorical variables, especially useful when you got unbalanced data. The next paper we published for the International Journal of Public Health was about using weighted effect coding in interaction models, and that was something Sweeney and Uring didn't explore. So this is really a new chapter in the book of weighted effect coding. Okay, to explain to you the weighted effect coded interactions, I'll just start with a first order regression model. As you can see, we have body mass index again as the dependent variable. We have over here the intercept, and that is equal to the sample mean because we weighted effect coded the categories for education, and we weighted effect coded the dummies female and male. And to get the estimates, we have to use the weighted effect coded restriction, saying that if we use a weight and multiply it by the B coefficient, and if we sum it over the three educational categories, we'll get zero. So one of the weights is negative, and the other two are positive. So as a result, the weighted sum of these B parameters equals zero. And we have also a restriction imposed upon the females and males, also saying that the weighted product of these of the sum of these weighted B estimates is also equal to zero. Okay, that is sort of wrapping up my first part of the presentation. But now we get something new. We also like to include the interactions, and the interactions are between females and lowest, middle, and highest education, and males and lowest, middle, and highest education. Well, in normal circumstances, you cannot estimate this equation because there is a lot of redundant information. But if we impose upon these interactions also the weighted effect coded restriction, saying that the sum of the weighted B parameters, the weighted interaction parameters, I should say, is equal to zero, then we will find the estimates. And we can do the same for the interactions between male and lowest, middle, and highest education, saying that the sum of the weighted B parameters again is 0. So we have 4 restrictions on this regression model. And if we impose those 4 weighted effect-coded restrictions, then we get estimates for our. I like to present the estimates now for the equation from the previous slide. I start out with the first order regression model. And we have over here education with the categories low, middle, and high. And we have males and females. And all these categories are weighted effect coded. So as a consequence, the value for the intercept is equal to 24.96. The estimates over here denote the difference between the category and the sample mean. So we have the low educated, and they have a average body mass index that is 0.81 higher than the sample mean. And we have the high educated over here, and they have a average body mass index of 0.60 below the sample mean, as indicated by the minus sign. And the middle educated, they do not differ from the sample mean in a significant way. Then we have over here the estimates for males and females. As you can see, the body mass index for males is higher compared to the sample mean. They are 0.30 above the sample mean, and the females are 0.27 below that sample mean, again indicated by the minus sign. Okay, well, this is a first order regression model, so without interaction parameters. Now, if we add the weighted effect coded interactions, the estimates will not change. So the estimates for education and the estimates for males and females I just showed, they will not change. Okay, let's include the interaction variables, and as you can see, the numbers above the horizontal line, they didn't change. So meaning that the first order model with the effects the estimate will not change if you change this to a second order model, including the interaction between females, males, and education. Well, when I explain interaction to students, I always find it hard to use the term main effects for all the estimates above the horizontal line, because in normal circumstances these estimates always relate to a certain subsample, for example all females or all low educated. But in this instance, where we use weighted effect coded interactions, I think the term main effect is just right here, because the effects over the horizontal line, they didn't change when we add interaction terms. They continue to be exactly equal to the first order model. Okay, well, but now what does the inclusion of these weighted effect coded interactions exactly mean? Well, if we take a look at this estimate of 0.21, this estimate means that if you are a female who is low educated, then we have to add 0.21. So 0.21 over here, we have to add that to this number over here, 0.81. So the low educated females, they do not have a body mass index of 0.81 above the sample mean. No, they have a body mass index that is almost 1 over the sample mean. So that's 0.81 plus 0.21. For the males, for the low educated males, it's exactly the other way around. If you are a male who is low educated, then your body mass index is a minus 0.22 on top of 0.81. So that's a lower BMI of almost 0.61 on top of the sample mean. So that's a lower value. meaning that the effect of education, in fact, is stronger for females. The difference between the low and the higher educated for females is actually um, stronger than the difference between the low and the high educated males. So for females, the effect of education is stronger than for males. That is exactly what this interaction table tells us. So if you run a interaction model with weighted effect coded interactions, they give you the extra number in the dependent variable on top of the main effect. And I think that is that's a very straightforward interpretation of interaction models, which normally are well, they are a bit difficult to understand, especially when you have the confusion of what a main effect actually is. Started this project, there was no software available to estimate our weighted effect coded parameters, let alone our weighted effect coded interactions. So we wrote our own software, and it's available in R as a R package, in Stata as a do. Both are very user friendly, and we have syntax in SPSS, which is a little bit less user friendly, I have to say. But it shows quite nicely how the weights are calculated within weighted effect coding. All this software, together with the data, is available through this link, together with the software that calculates the estimates for an interaction between categorical variables and a interval variable. That's a combination I did not address in this presentation. Well, just to summarize, I think it is a relevant question. When do we actually use weighted effect coding? And well, I think a necessary condition is that the data are unbalanced. So if you have a categorical variable with very different group sizes, so with very different number of observations, then weighted effect coding is to be preferred over effect coding, because the last method doesn't take into account the different group sizes. So then weighted effect coding makes sense. It also makes sense in case you got non-directional or rivaling hypotheses. Then dummy coding is a less appropriate method, um, because there is no clear reference category um, to use in your regression analysis. So testing against the sample mean would be a more appropriate approach. And the last reason is that when you use dummy coding, there's always this choice you have to make which reference category should be chosen, and that looks sometimes a little bit arbitrary. So if you like to avoid this arbitrary choice of a reference category, then weighted effect coding comes in very handy, I think. Um, and I would like to add that if you are testing with a weighted effect coding method, then the testing you are doing actually is more conservative uh, than testing with dummy coding, because if you use dummy coding, yeah, it's a sort of black against white comparison between one category and the other, which makes it more likely that your research hypothesis is corroborated. So if you like a more conservative test, then you will test all the categories of your categorical variable against the sample mean. To end this presentation, I thought it would be nice to give you a graphical presentation of the whole problem. We have over here a number of categorical. We have one categorical variable, and we have some. Let me see, some seven categories of that variable, and I showed them as a circle, and the larger the circle is, the more observations that the particular category has. And if we would just ignore um, the uh, uh, the size of the circle, then uh, uh, the red line over here would be the unweighted baseline, and we got all effects would be compared to that red line. So that would be an unweighted effect, not taking into account the fact that we have different numbers of observation. If you would take the differences in the sizes of the circles into account, the weighted baseline would be somewhere over here. And if we would now um, estimate the weighted effect, then we see that we get quite a different effect for that particular category. So I think in a nutshell, that is the difference between using effect coding and using weighted effect coding, whether you consider that baseline as a difference in mean. That was the first part of my presentation, or whether you would like to see this as a difference in effect in an interaction model in the second part of my presentation. Um, well, yeah, that's the difference between effect coding and weighted effect coding, hence that we coined the title of this presentation, When Size Matters. And if you got unbalanced data, of course, the number of observations will make a quite large difference. Okay, well, that was the end of my presentation. Thank you very much for being here and for your attention. And hopefully weighted effect coding can be useful in your own research. Thank you very much.